Hi everyone, I'm Professor Burgasser, and in this video we're going to look at an alternate equation for the case of constant acceleration, how we can relate some of our physical quantities in a way that's a slightly different equation than we've used before. So in a previous video we looked at how we could derive the velocity and the position as a function of time for the case of constant acceleration, and in particular in this case for one-dimensional constant acceleration where we've gotten rid of the vector notation. Now, using these expressions often requires some knowledge of the time on which these measurements are made. So for example, the time that a ball reaches its height or a time that something hits the ground. But we may have cases where we don't know the time explicitly, but we want to figure out how velocity changes as a function of position, for example. Well, in that case, we can actually get rid of the time component by combining these equations to form a third equation that's equivalent. So to do that, we actually have to isolate the time component. So I'm going to start with this first equation, which is the velocity as a function of time is equal to initial velocity plus at. We can use some algebraic work to turn this into an expression for the time given as a function of the difference in velocity divided by the acceleration. And then we can plug this quantity back into our equation over here. So if I'm going to actually take my position coordinates here and define our original displacement is equal to r of t minus r of 0. All right. And then I'm going to go ahead and plug in my expression for time into the places that it appears in this equation. So v of t minus v of 0 over the acceleration plus 1/2 times the acceleration v of t minus v of 0 over acceleration quantity squared. Okay, and I'm going to now simplify this part of the equation a little bit. Notice that both sides have a 1 over acceleration. Both of these expressions here have 1 over acceleration. One of these accelerations cancels with the one out in front, but you're left with 1 over a on both sides. So I'm going to take that 1 over a and multiply it on both sides, so I'll get a delta r. And then I'm going to expand out these expressions. We get v of 0, v of t minus v of 0 squared plus 1/2, and I'm going to expand out my quadratic equation here, 1/2 v of t squared plus 1/2 v of 0 squared, and then minus 2 times v of t minus 2 times v of t, v of 0 times 1/2 gives me a v of t, v of 0. All right? And notice we can cancel out our first and last terms. And in fact, we have a minus v, the initial velocity squared plus 1/2 the initial velocity squared. So we're going to end up with a minus 1/2 velocity squared. That gives us an extra 2. So I'm going to combine all this stuff up together. Get the 2 out in front here. So multiply both expressions by 2. We're going to get v of t squared minus v of 0 squared. Or, if we rewrite this, the velocity at some time t is equal to our initial velocity squared, both those quantities squared, plus 2 times the acceleration times the displacement. Okay, so that was a quick derivation of how we go from our original velocity and position as a function of time to an expression that doesn't actually explicitly contain time in the equation. All right, it tells you the difference in the velocities squared instead of difference of velocity, and then that's equal to 2 times the acceleration over the displacement at which that acceleration was applied. Now, keep in mind this is only true for constant acceleration. It's not something that's generally true for an acceleration that depends on time. And this is also going to be something that we see later on when we talk about the work-energy theorem. In fact, these velocity squareds are going to match up with our expressions for kinetic energy, and this part is going to look a lot like our expression for the work done on an object. So we'll see this expression again, but just keep in mind that we now have 3 expressions that we can use when we're trying to solve for the motion of an object under the case of constant acceleration. So to see an example of how we might use this alternative expression for 1D acceleration, let's consider the following problem. Let's imagine that we've shot off a bottle rocket. It makes a total height of 150 feet, and we want to know how fast the rocket was going when it was initially launched. So let's break down this problem. What kind of problem is it? It's only moving up and down, and we're ignoring air resistance. So this is a 1D constant acceleration problem. All right, so we can write that down, 1d constant acceleration. And then we should write down the things that we know. We know that the total displacement was 150 feet. That's the height that the rocket went up. And we know that the acceleration is just that equal to minus 9.81 meters per second squared. That's just our gravitational acceleration. And we can ask what was the velocity. We were asking for the velocity at the start, but we can also ask what's the velocity at the top of the motion. And of course, if it's reaching the top, it's not going to go any further. So at that point, the velocity is sort of maxed out. I should take that back. The distance is maxed out, but the velocity has gone to 0 at that point. So we know that the velocity at some time t, which is the maximum of our height, is equal to 0 meters per second. And then what are we trying to find? Well, that's just the initial velocity as a bottle rocket is launched up, right? So now with these knowns and understanding what kind of problem we're looking for, we can evaluate which one of the equations we want to use. And of course, the whole point of this is to do an example of our alternative form, so that's the equation we want to use. So let's write down that expression. We had v of t squared is equal to v of 0 squared plus 2 times the acceleration times the displacement. Putting in our numbers, we know that the total displacement is going to be 150 feet. Now, let's take a moment here to convert to meters because we've got mixed units, 150 feet and 9.81 meters squared. So in fact, let's rewrite delta r as 150 feet times the conversion factor, and that's just 0.305 meters per foot. All right, there's about 3 feet in a yard, and a yard is somewhere around a meter, so this is a good estimate of the distance. And so we can convert that out, and that turns out to be 45.7 meters. And I'm keeping an extra decimal place here just so I don't have any round-off error when I get to the end of my problem. Of course, at the end of my problem, I have to make sure that my answer has the same number of significant digits as the numbers that I'm given. Okay, so now we have everything in the same units, and we can start to write down the expression. Our velocity at the top of the motion is, of course, 0. That's equal to the thing that we're looking for, the initial velocity, plus 2a delta r. A is minus g, because it's in the opposite direction of motion. So this is going to be minus 2 times 9.81 meters per second squared. And then we have our displacement, which is 45.7 meters. All right? And if we look at the units, of course, we're going to get meters squared per second squared, and that's the units for velocity squared. So we can write all of this out, v of 0. I'm actually going to just move that over and then take the square root of this quantity, 2 times 9.81 meters per second squared times 45.7 meters, all square root. And when you go through the calculation, what you find is that this number, to the right number of significant digits, is 30 meters per second. So that's the initial velocity of the rocket in order to reach a height of 150 feet, or 45.7 meters. Now, this is a good time to check to make sure this answer makes sense. If we look at the total height here, 45.7 meters, and we started off at 30 meters per second, to go from 30 meters per second to 0 meters per second, and you're accelerating at minus roughly 10 meters per second squared, that means you're only going to be in the air going upward for about 3 seconds. So 3 seconds up, 3 seconds down. And so that gives us an estimate of the time. And at 30 meters per second, and assuming we're going kind of the average of that, because it goes from 30 to 0, so about 15 meters per second on average for 3 seconds, should take us about 45 meters. And that's indeed the distance we go. So you can do these sort of checks to make sure that the answer at least makes sense with the numbers that we're given.